Hello everyone, how's it going? Here we'll be discussing chapter 4.9, which is antiderivatives. And here let me just start off by saying an antiderivative is a function capital F of x for a given function lowercase f of x, such that capital F prime is lowercase f of x. Basically, it's a function whose derivative is the original function we're given. In other words, it's just the opposite of derivative. So kind of like what the word sounds like, antiderivative. So here I give some examples and then we'll generalize it with something we'll see from powers of x. But let's see, we just kind of want to think, what function has derivative these? So let's try to undo derivative here. I'll write my answers in red, so let's see if we can get some progress going here. So what is the derivative of, or antiderivative of 2x? What function has derivative 2x? The first thing to note is that the power here is x to the 1. When you take derivatives, the power reduces by 1 because of the power rule. So that means the function whose derivative is this must have 1 higher power. So if you add 1 to this power, you get x squared. And that's a good guess. That's a good place to start. And as it turns out, this actually works because derivative of x squared, notice, is 2x to the 1. So we're done there. Awesome. What about cosine? Well, derivative of cosine is negative sine, derivative of sine is cosine, and that's it, actually. Because since derivative of sine is cosine, and that means the antiderivative of cosine must be sine, again, because the derivative of this is what we started with. So that's not too bad once you see that. Now this one becomes a little complicated. Something we'll actually get a handle on real soon, but when you first see these kinds of things, this will start to make you think a little bit. The way I describe this one will help a lot because we'll see that our guess would be x to the 6th because derivatives reduce the power by 1. So the antiderivative of this would probably be 1 power bigger. So a good guess would be x to the 6th. There's a little bit of a problem though, and that's of course that when you take derivative of x to the 6th, you don't get x to the 5th, you get 6x to the 5th. That, as it turns out, isn't too big of a problem because since we have constant multiples coming for free from constant multiple rule of derivative, then we can say that if there was a 1/6 here, the 6's would cancel and we would indeed get our original result, x to the 5th. So if this is multiplied by 1/6, then derivative of that is 1/6 times derivative of x to the 6th, which is 6x to the 5th. The 6's cancel and we indeed get x to the 5th. So this is actually the answer. And this idea leads to the anti-power rule, or rule for antiderivatives, power rule for antiderivatives. And it says that the antiderivative of x to the n, so let me denote that by an arrow with AD on top, AD for antiderivative, is, well, 1 over n plus 1, x to the n plus 1. Awesome. And let me box this actually. One thing more I'd like to say here is that I'm using this arrow notation with AD for antiderivative instead of using this capital F notation. In my opinion, personally, this is kind of terrible notation for antiderivatives. Later on in chapter 5, though, we'll be developing more language on that, so it'll be better. Kind of like the equivalent for derivatives being d over dx of, instead of the prime notation. This is kind of like equivalent to prime notation. But in chapter 5, we'll develop kind of a Leibniz style notation, which will allow us to write it with equality instead of these arrows. But for right now, we'll be using these kind of arrows, if that's okay. So now we're going to be taking a look at some generalizations of this. And in fact, something I want to note here also is I may or may not have said that the antiderivative of x to the n is this. And that technically is an incorrect statement. Why is that? It's because here I say an antiderivative of a function is this. So this is an antiderivative, not the antiderivative. In fact, not one function has a single antiderivative. You can find the most general antiderivative, and the reason why this scenario happens and why it's a little technical, it's not too bad once you start to see some examples. So for example, derivative of x squared is 2x, but are there other functions whose derivative is 2x? And yes, there are. For instance, if we were to add, let's say, a plus 5 here, since derivative of 5 in its own right as a constant term is 0, then derivative of x squared plus 5 is also 2x. So for that reason, the fact that derivatives of constant terms are 0, we kind of get this issue happening. So we'll actually generalize this in a second. Basically, you just write plus c for everything to find the most general antiderivative, and then you carry on from there. So along with writing that statement, I'll actually generalize some more rules, kind of like this one, based on what we know from derivatives. All right, so here I've written basically what we just spoke about. If f of x, capital F of x, is an antiderivative of lowercase f of x, then the most general antiderivative, most general is a key phrase here, of f of x is capital F of x plus some constant capital C. So get used to, at this point, writing plus c anytime you take antiderivative. In fact, that's kind of a joke amongst people getting used to calculus and calculus 2, is don't forget plus c, because it comes up that often. Anyways, let's recall here some derivative rules. So I have derivative of ax is just a number in front of a, so a is a constant. Power rule, constant multiple rule, summation rule, e to the x, sine goes to cosine goes to negative sine, tangent goes to secant squared, secant goes to secant tangent, ln goes to 1 over x, or x to the negative 1, tangent inverse, or arctangent, goes to 1 over the quantity 1 plus x squared, to name a few. Now these are the most common ones that come up, which is why I wrote only these. So you may think, okay, what about cosecant, cotangent, sine inverse, for example, or the hyperbolics? I only wrote these because they come up most often than the others, or more often than the others. Otherwise, also, it's more to write. But anyways, what we're going to do is we're going to develop some antiderivative rules, basically by using these in reverse. Now, we're not going to get too technical. We're basically just going to be going in reverse here. The most technical we'll be doing is essentially the power rule that we just developed in the previous board. So here, derivative of a is ax, or antiderivative of a is ax. Antiderivative of x to the n we saw was 1 over n, x to the, 1 over n plus 1, x to the n plus 1. Antiderivative of a constant times f of x is a constant, c, times capital F of x, which is the antiderivative of f. Antiderivative of a sum of two functions is the sum of the antiderivatives, capital F plus, let's say, capital G of x. E to the x has antiderivative itself, of course. Now this is where things get a little funny. So the antiderivative of sine is cosine. Well, derivative of sine is cosine. So that means the antiderivative of cosine will be sine. That, I think, is clear. The antiderivative of sine, though, must be negative cosine, because derivative of cosine is negative sine. So just to get a better understanding of this, if you were to take derivative of negative cosine, since derivative of cosine is negative sine, you get a double negative sign, which is positive sine. So that's the reason why that works. So it's almost like going in reverse. Cosine is no longer the bad guy, now sine is the bad guy, which is the way I think of that. Now notice I don't have antiderivatives of tangent or secant listed out. Those, as it turns out, are pretty complicated to do, but we'll be discussing later on. Mostly those are looked at more in Calculus 2 than Calculus 1. But at least we can say the antiderivative of secant squared for sure is tangent. And antiderivative of secant tangent is, of course, just secant, because derivative of secant is secant tangent. Antiderivative of 1 over x, or x to the negative 1, is ln of x. We have to write absolute value, though, and it's a little funny. But notice that here x can't be 0, and you can have ln of 0. So that's okay. That part is fine. But you can take the reciprocal of a negative number, but for ln, you cannot have natural log of a negative number. So for that reason, we take absolute value, just in case the inside is negative. Just in case the denominator is negative. Which now sounds funny, but it's an idea we'll kind of be getting used to, okay? And here, antiderivative, finally, for 1 over x plus, 1 plus x squared, I should say, is arctangent or tangent inverse of x. Now, from the above statement, we need to write plus c for all of these to be most general. So I'll just do that just so we get used to it. So this is plus c, plus c, plus c. I know there are two c's here, but pretend one's capital and one's lowercase, I guess. So we'll get used to writing plus c each time. And you don't need to write more than 1 plus c in any given statement or any given expression. Only write 1. Of course, if you have 2 plus c's, that's a constant plus a constant is still another constant. So I know that sounds weird, but again, more ideas we'll be getting used to. So now we're going to look at some examples and see which of these apply. Something I must say before moving on, though, is that people very often get confused between this and this, because this is technically a power. So something I want to say here is that for the power rule, antiderivative power rule, you cannot use it when n is equal to -1. Because notice, if n was equal to -1, then the antiderivative would be 1 over 0 x to the 0, which is undefined. So when you have a -1 power, don't use the anti-power rule, use the natural log antiderivative rule. Okay, so now we'll see some examples. All right, so here we have these two examples. They're kind of different, but basically what they're asking for is an antiderivative type scenario, but the wording's a little weird. So it says final functions g of x such that g prime is this. So we want to find a function whose derivative is this, hence antiderivative. And we can do that term by term. The only issue is we have a quotient here, and I haven't given you a quotient rule for antiderivatives. But one thing you can notice right away is that this radical x may be bugging us. So I'm going to change that, if you don't mind, to 1/2 power, like we're kind of used to for derivatives. And then you may notice that if we split this fraction up as the first 1 over x minus the second 1 over x, then we can actually rewrite these as each powers each. So we get 4 sine of x plus 2x to the 4th, and then minus x to the -1/2. Now here we can find an antiderivative. So this is still g prime of x. And now we can say by antiderivatives that g of x must be just a function whose terms, I guess, are antiderivatives of each of these terms. Antiderivative of 4 sine is -4 cosine, because antiderivative of sine is negative cosine. So antiderivative of 2x to the 4th would be, well, you have to add 1 to the power, so it's x to the 5th over 5. So it's going to be 2/5 x to the 5th, just like that. Now antiderivative of x to the -1/2, if you add 1 to the power here, so kind of think of this, x to the -1/2, its antiderivative is x to the -1/2 plus 1, which is +1/2, divided by that new power, -1/2 plus 1. So really what you end up getting is x to the +1/2 over +1/2, so 2x to the 1/2. In fact, the better way, in my opinion, to handle these fraction powers is to add 1 first and then multiply by the reciprocal in front. So if you add 1 to -1/2, you get +1/2. The reciprocal of +1/2 is 2, so you get -2x to the 1/2. And if you want to write that at this point as radical x, we can do that, but I'll leave it like this, I think. And then, of course, we want to find all functions, so we need our plus c. Now remember that we technically get a plus c for each of these terms, but what I said earlier is that just write plus c at the very end, because technically those plus c's would be different. So you'd have a plus c1, plus c2, plus c3, and 3 constants added together is just one new constant, call it capital C. So this works out, and I'm going to leave our answer like this. And again, if you don't like that x to the 1/2 part, you can rewrite that as radical x if you'd like, but I'll leave it like that. Awesome, and now we'll move on. So now here we want to do the same exact thing, only we're given this so-called initial condition. Now what this is for basically is to find the plus c that we'll end up with. Now the other thing is that we may need to rewrite this to make it look easier. E to the x is not too bad. So f prime of x in this case is e to the x, that term's okay. Its antiderivative will just be e to the x, so we'll deal with that shortly. But then this guy is this weird expression to the -1, and that looks like a chain rule scenario, and I haven't shown you an anti-chain rule yet. So the way we'll handle this is, of course, just write it as 20 over this denominator, which is 1 plus x squared, because it's to the -1, it's the denominator. And this should now remind us of 1 over 1 plus x squared. In fact, really, if you wanted to, you can write this as 20 times a quantity, 1 over 1 plus x squared. And this is actually the way you should be seeing it, actually, because we know the antiderivative of this, it's tangent inverse. So now we can say by antiderivative rules, the antiderivative of f prime is just f, which is e to the x plus 20 tangent inverse of x plus c. Now, I would box this here, but in this case, we're actually given an initial condition. So how can we use this initial condition? Well, it says f of 0, and usually, remember, we have f of x, so that means we want x to be 0 in this case. And if you let x equal to 0, what happens? Let's see. We end up getting f of 0 over here equals e to the 0 plus 20 tangent inverse of 0 plus c. Now, e to the 0 is negative 2, or f of 0 is negative 2, sorry. E to the 0 is 1. Tangent inverse of 0 is 0, so that's 20 times 0. And then plus our constant c, which is not affected by any change in x. Now this is 0, c plus 1 is this. Subtract 1, you get c is negative 3. Fantastic. So now plugging this result back into this result, we end up getting our final answer finally, is that f of x is equal to e to the x plus 20 tangent inverse of x minus our constant 3. Well, plus our constant negative 3, but I wrote it like this. Fantastic. And now we'll move on to see some more examples. It'll be kind of similar, but maybe a little more challenging than these. All right, so here's an example where we're given the second derivative, not the first derivative. So what this kind of tells us is that we have to antiderive twice, or differentiate twice. So the first antiderivative will yield f prime, the second will yield just f finally. So we can take the antiderivative of each term as is. There's no prep work like in the previous problems. So that's good. So let's just say that f of x, or I guess f prime of x in this case, because we lose one prime when we antiderive, or antidifferentiate. We get antiderivative of this, which is 12 over 3x to the 3 plus 6 over 2x to the 2 minus 4x. So I hope we see how I got this. I'm just using those antiderivative rules that we developed earlier. And if you kind of simplify a little bit, you get 4x to the third plus 3x squared minus 4x plus c. Now this is f prime, so we can't actually use any of these evaluations yet because none of them are f prime of something, it's just f of something. Which is possible you can have an initial condition that actually involves f prime and not just f. We'll actually see an example of that after this. But now we need to do antiderivative once more to get, well, to our original function f. So let's see, antiderivative of f prime is just f, which is, well, you add 1 to the power, that's x to the 4, and this will be 4 over 4 now. Add 1 to the power here, you get x to the third, that's 3 over 3. So these are actually looking to be pretty nice. The power here is 1, add 1 to the power, you get 2 divided by 2. C is a constant, so you multiply it by x, and then we get another constant here. I'm not going to write plus c though. You could write plus c1 or c2 or something like that if you like, but I'll use k for constant. That's a joke, obviously. But yeah, so let's see if we can reduce a few of these. So this is just x to the fourth plus x to the third minus 2x squared plus cx plus k. And great, so now we have these two constants, unknown constants, but we can use hopefully our initial conditions to figure out what's what. So for our first initial condition, notice that our x value is 0. So when we set x equal to 0, we get f of 0 is equal to, let's see, 0 to the fourth plus 0 to the third minus 2 times 0 squared. Obviously these are all going to be 0 because they're just multiples of 0 basically, plus c times 0, which is also 0, plus k. So f of 0 is literally just equal to k, but f of 0 is negative 4. So there we go, we get negative 4 is equal to k. Awesome. And this is kind of our answer. We're just trying to find out the unknowns c and k. So far we found k. But now for the second initial condition, we need to plug in x equals 1 now into our function here. So we get f of 1 is equal to 1 to the fourth plus 1 to the third minus 2 1 squared plus c times 1 plus k, but we know k is negative 4, so I'll just write minus 4 if that's all right. And f of 1 is equal to 1, so we get 1 equals 1 plus 1 minus 2 plus c minus 4. And notice the 1 plus 1s are just 2, which cancels with this 2. And if we add 4 to the other side, we right away get that c is equal to 5. Perfect. So now, knowing k and knowing c, we can plug these into our function, and then right away get our answer is just x to the fourth plus x cubed minus 2x squared plus 5x minus 4. So let me write that now, and then we'll be done with this example finally. So we got x cubed, x to the fourth plus x cubed, there we go, minus 2x squared plus 5x, and then minus 4. Whew. Nice. Perfect. Went kind of a little off the board there, so let me just kind of tilt the camera a little bit so we can see more of that. There we go, looks better. And now we'll move on to see one more example finally, and that will really be the end for section 4.9. Right, so I said to do one more example, but I thought we should do two, because I really want to see an example that involves this. Otherwise, I don't feel I did the topic justice. But let's see. So I want to find the antiderivative once to get f prime, and that's just adding 1 to the power and then dividing by that power. So dividing by -1 makes it negative. Do it again. The only issue here, and this is what I definitely wanted to go over, is that you can't use the power rule here, and I mentioned it earlier. You would add 1 to the power, get 0, but you can't divide by the new power 0, because it'd be undefined. So instead we look elsewhere in our antiderivative rules, and the antiderivative rule that you should find is that the antiderivative of 1 over x, which is the same as x to the -1, is ln of absolute value of x. But here I'm not going to write absolute values, and the reason being is that it's given that x is bigger than 0, so its absolute value is itself. Now, when you antiderive the first time, you get a plus c. When you antiderive the second time, that goes to cx, and you get a new constant like we did earlier, which we'll call k. Now, here we'll use these initial conditions, much like we did with the previous problem. F of 1 is negative ln of 1 plus c plus k. Okay, good, so far so good. Ln of 1 is 0 actually, and this is 0. So that means 0 is equal to c plus k, meaning that c is equal to negative k, or something like that. Which isn't very useful, but we'll kind of see with the next value, with the next evaluation, it will be okay. So now we'll get f of 2 is equal to, well, this is our function we're using, so we get negative ln of 2 plus cx, but c is negative k, so it's going to be negative kx. There we go. Plus k. Also, we're plugging in 2, so it's going to be negative 2k. Hope that wasn't too confusing. But yeah, it's because it's c times 2, but c is negative k, so it's negative 2 times k. Okay, good. So now these, of course, combine to negative k. This is 0. So all we need to do now is just add this to the other, well, I guess we can add k to the other side. And we get k is equal to ln of 2. Perfect. So now we have all of the pieces in line, so now we can piece it together. We get f of x is equal to negative ln of x minus ln of 2 times x, like that, and then plus k, which is ln of 2. So it was a little funky looking, but it's not too crazy, I guess. But again, I really wanted to showcase an example that involved natural log, because when it comes up, it confuses people. So don't let that get the better of you. And now onto this one, which is really what I wanted to actually do, because this, of course, involves a triple derivative, which we'll have to antiderive 3 times, and our initial conditions involve derivatives. So this is a good example to see. Now, I'm going to do this in a similar way I did this, just kind of antiderive each time, make sure we have plus c and so on. So every time we take the antiderivative, we lose a prime. Antiderivative of cosine is positive sine, we get a plus c. Antiderivative of sine is negative cosine of x. Antiderivative of c is cx, we gain another constant, let's call it k. And then, by the way, at this point you can use these one at a time if you like to get rid of the c and k, and then you can reuse the labeling. But I'm just going to do it this way because I think it's kind of fun, more fun in my opinion. But that's just me. Now, antiderivative of negative cosine is negative 1 times the antiderivative of cosine, which is sine. So this is negative sine. Antiderivative of cx is c over 2x squared, because antiderivative of x to the 1 is 1/2 x squared, so that's good. Antiderivative of k is kx, and then we get a new constant, which, I don't know, you can call whatever you want. I'll just call it L. Doesn't really matter what you call it. In fact, let me use capital L, but that's okay. So now, for f double prime, we have an evaluation. So we'll plug in 0. So we get f prime of 0, which is 3, is equal to sine of 0 is 0, plus c, so that means c is equal to 3. So I hope that wasn't too hard to follow. I kind of skipped a little bit, but yeah, I'm just plugging in 0 everywhere, and then f prime of 0, double prime of 0 is given to be 3, so we'll use that here and we're good to go. So now here, when we plug in 0, f prime of 0 is 2, so that's going to give us 2 is equal to negative cosine of 0. Cosine of 0 is 1, so that's negative 1, plus ck, not ck, plus cx, but x is going to be 0. So that goes away actually, so plus 0 plus k. There we go. And that means k must be, well, 3, because if you add 1 to this side here, like that, these cancel and you end up getting that k is equal to positive 3. So that hopefully is not too bad to follow either. And now finally for the last one, when we plug in 0, what's kind of nice here is that everything goes to 0. F of 0 is given to be 1, so we get 1 is equal to sine of 0 is 0, 0 squared times anything is 0, 0 times anything is 0, so we just get 1 is equal to L. And now plugging things into our final function here, we're good. And we get f of x is equal to negative sine of x plus 3 over 2 x squared, make that look a little nicer, there we go, plus 3x plus 1. Now something I haven't said yet at this by this point in time is you can always check your answer by taking derivative and making sure if it satisfies these initial conditions. So if you take derivative once, then you get, let's see, derivative of negative sine is negative cosine. That's going to be 3x, and that's going to be 3. So you literally just get this. Derivative of negative cosine would be sine. So derivative of 3 is 0. Derivative of 3x is just 3. So there we go. And then derivative of sine is cosine. So you just get cosine, and then 3 goes to 0. So you kind of see that you can ladder it back, so to speak. And check to make sure that this satisfies these. But you'll have to check with derivatives. In this case, for this one, we could have used these two. Like for instance, when you plug in 1, you get that's 0. That's going to be negative ln of 2 minus ln of 2. Or I guess negative ln of 2 plus ln of 2 cancels out, so you get 0. When you plug in 2, you get negative ln of 2 plus ln of 2 cancel. Yeah, so look at that. Actually checking was allowing me here to kind of check my answer here, and I made a little mistake. So it's good that I saw that you can obviously check this and discuss that. So the mistake I made is that for whatever reason I didn't bring down this negative here. So adding k to the other side would mean that k is equal to negative ln of 2. So that means this would become negative and this would become positive ln of 2. Now this makes sense again because using the initial conditions, when you plug in 1, you get ln of 1, which is 0, that's 0, and you just get negative ln of 2, no, I'm sorry, you're plugging in 1. It's ln of 2 minus ln of 2, which is 0, so that works, good. So now plugging in 2, we get negative ln of 2, minus ln of 2 is negative 2 ln of 2, but when this is 2, because x is 2, you get 2 ln of 2 minus 2 ln of 2, and that's 0 actually. Wow. So it was good that we were able to catch that using checking these initial conditions, which is nice. You can always do that, so you can catch any mistakes, if any. So, right. So with that being said, that's all I wanted to say for 4.9. I'll see you in the next videos when we'll be discussing Chapter 5 finally. So this is the last thing to discuss in Chapter 4, which will really set the tone for this change in the class. So the class will now focus mainly on antiderivatives. So I'll see you in the video for Chapter 5, the videos for Chapter 5. It's going to be a lot of fun because we'll be developing kind of more language as far as better ways of describing antiderivative and relating it to something kind of analogous to how derivatives relate to tangent lines. We'll see something similar with that. It's going to be a lot of fun, like I say. So I'll see you in the videos for that. Thanks for watching, and I'll see you then.